in this problem, if we read it from another point of view, we can see that our objective function z consists of two parts. One part consists of our decision variables x1, x2, where their coefficients 0.4, 0.5 are relatively small. The other part consists of our artificial variables x4, x6, while their coefficients m are very huge numbers. So numerically, this m is very big compared to the coefficients of our original objective function. These two decimals are actually negligible to m. So with these small numbers, if we use computers to apply simplex method, some numerical errors may happen during the computation. So in order to avoid such errors in the big M method, we would introduce two-phase method. Two-phase method is another way of solving linear program problems and deal with these big M's. But this is an easier way to avoid numerical errors. And by name, two-phase method contains two phases. And each phase, we optimize a different objective function. Phase 1 of the two-phase method is to minimize the objective function that consists of our artificial variables only. And since this is a minimization problem, our objective function has to be with the minimum value when x4 and x6 be 0. And then the phase 2 of the two-phase method is to minimize our original objective function under the condition of phase 1, when x4 and x6, our artificial variables, are zeros. So with this idea, we can talk about the basic process of the two-phase method. To initialize the two-phase method, we first revise our constraints of the original problem by introducing artificial variables as needed to obtain an obvious initial BF solution for the artificial problem. And then, in the phase 1, we use the simplex method to solve the linear program problem of minimizing z, while this objective function is the sum of all the artificial variables subjected to the revised constraints. And then the optimal solution obtained for this problem ideally would be with z equals 0 will be a BF solution for the real problem. And for example, if we want to minimize, this is our original setup for the big M method. Since M is very large compared to these two coefficients, if we want to use the two-phase method, we will split the objective function into two parts. In the first part, we want to minimize the sum of only the artificial variables x4 plus x6 with all the revised constraints. All the constraints still stay the same. And then in the phase 2 of our simplex method, we would drop the artificial variables because now they're all zeros anyways. And then start from the BF solution obtained at the end of phase 1 and use the simplex method to solve the real problem. So for example, in our rounding example, if we want to minimize our original, we just need to minimize our original objective function with all the constraints. And note that in these constraints, we dropped our artificial variables x4 and x6. Now let's look at an example how the two-phase method actually works. So we say in phase 1, we have all the revised constraints, and we want to minimize the objective function, which is the sum of all the artificial variables. And then, of course, we want to put our problem in the standard form. So we rewrite our objective function. x4 and x6 are the artificial variables, so they are the initial basic variables, and they should not appear in our original objective function. So we want to make some changes and so that our objective function is in terms of non-basic variables, or the rest of the variables only. So x4 can be expressed by this constraint, 6 minus 0.5x minus 0.5x2, and same for x6, so so solve for x6 from the last constraint, and then substitute them into our objective function to obtain an expression of z in terms of non-basic variables only. And then change z to the maximum form because this is the standard form required for the simplex method. And then build up the simplex tabular by finding all the coefficients, all the basic variables, all the non-basic variables, and then all the right-hand side. And then with this tabular, again, we just apply the optimality test. Equation 0 contains negative coefficients. So we pick the biggest one in absolute value and then do the minimum ratio test, find out the leaving basic variable and the entering basic variable, do Gaussian elimination, make that column unit. And then after we do the first iteration, again, do the optimality test. We have a negative coefficient in equation 0 and then do the minimum ratio test, find out the corresponding leaving variable, and then make that column unit using the Gaussian elimination. After we repeatedly apply this iteration, eventually we'll have the tabular in its standard form, where all the coefficients in equation 0, except possibly for z, because it's our objective function, are all non-negative. Then we say we can stop. The simplex method gives us an optimal solution at this point. As we expected, the optimal solution for our the value for our objective function at this point is 0, and then we can correspondingly find out the values of our basic solutions, x1, x2, and x3, and then x4, x6, the artificial variables will take the value 0. Okay, so this is phase 1 of our two-phase method. After we reach this point, we say that the solution, the values of x1, x2, x3 equal to these values is indeed a BF solution for the real problem, because all the constraints we use, all the equations we use in the simplex method are actually the fractional constraints for our real problem, because x4 and x6 are zeros anyways. Okay, so we finished our phase 1 by finding the minimum value of our objective function being the sum of the artificial variables, that is 0, and then we need to continue to phase 2. Phase 2 means that we want to drop our artificial variables and consider the real problem. So this is our original final simplex tabular we obtained from at the end of phase 1. So we drop the artificial variables just to remove these two columns and obtain a new tabular. And this is the tabular we will use to start the simplex method for phase 2. In phase 2, remember that now we want to optimize our original objective function, minimum of z equals 0.6x1 plus 0.5x2. Again, put it in the standard form of maximizing negative z minus 0.4x1 plus 0.5x2 equals 0. Put it in the standard form, and then the rest of our tabular remain the same, but our objective function is changed. So we have to replace the coefficients in equation 0 of our final simplex tabular by the new coefficients. So we make this change and then write our new equation 0 with coefficients -1 for z, 0.4 for x1, and 0.5 for x2. So this is where we start the simplex method for phase 2. So to start the simplex method, we recall that even though this table looks like that, all the coefficients in equation 1 are non-negative, it seems it passed the optimality test. However, remember that we now have these basic variables x1, x2, x3. In the standard form, their corresponding columns have to be unit, meaning that we only have one in that column and all other values should be 0. So even though these are positive, it's not in the proper form because we introduced these two coefficients and then these two columns are not unit columns anymore. So before we start our simplex method, we need one more iteration to make these values 0 by using Gaussian elimination. So after we multiply and then do the appropriate elementary row operations, making all these columns proper, we say, well, now in equation 0, there is a negative value. And then we choose this column to be our pivot column and then do the minimum ratio test and then make that column unit by Gaussian elimination. And then after this iteration, we say, well, now our table is in the proper form with all the coefficients in equation 0 non-negative except the coefficient of our objective function z. So the simplex method terminates, and at this point, we can read the value of our basic variables, x1, x2, x5 from the right side, and also the value of our objective function, negative z equals negative 5.25. So z equals 5.25. And then thus from this way, we can use the two-phase method to find out the value of the optimal solution to our original problem and then the corresponding z value. Okay, so as we saw from the previous examples, we say a two-phase method streamlines the big M method by using only the multiplicative factors in phase 1 and by dropping the artificial variables in phase 2. The big M method could combine the multiplicativity and additivity factors by assigning an actual huge number to M. But this might create numerical instability problems if we use computers to help us. So for these reasons, the two-phase method is commonly used in computer codes. But if we want to compute some linear program problem by hand, of course, we can choose either way as we like. Okay, next, we say that given a linear program problem, if we can easily identify an initial BF solution, we can proceed to the simplex method directly. However, if the initial BF solution is not obvious, we can introduce the artificial variable technique to construct an artificial problem use of either the big M method or the two-phase method. We can have an initial BF solution and then we can start our simplex method. On the other hand, if the original problem has no feasible solutions, then either the big M method or phase 1 of the two-phase method yields a final solution that has at least one of the artificial variables greater than 0. And this means there is no feasible solution. Otherwise, if there are feasible solutions, all the artificial variables should be 0. Next, we talk about some other situations we may encounter in the simplex method. So we talked about how to make the standard form of the objective function. If it's in the minimum form, we change it to max negative z. If we have equations or bigger than equal to forms for the constraints, we can introduce artificial variables to make them in the standard form. Next, we talk about the non-negativity restrictions for the variables. So in most of the cases, in practical, negative values for the decision variables would have no physical meaning. So it is necessary to include non-negativity constraints in the formulations of their linear programming models. So any problem containing variables allowed to be negative must be converted to an equivalent problem involving only non-negative variables before the simplex method is applied. Simplex method applies only to non-negative variables. So to deal with variables with negative values, there are two cases. First, if a decision variable satisfies the constraint of the form xj bigger than or equal to lj, where lj is some negative constraint, we can convert this constraint by using a change of variables and let xj prime equal to xj minus lj, so that xj prime is bigger than or equal to 0. And then the expression of xj equal to xj prime plus lj will be substituted for xj throughout the model. Second, if our variable has no lower bound on the negative values, we cannot use the method as before, but then in this case, we can simply rewrite our xj as xj plus minus xj minus as two parts, while both parts are non-negative. So for example, if we want to reformulate our problem like this and change all the values to be non-negative, since x1 is unsigned, we can just simply consider it as a difference of two variables, while both variables are positive. And then the expression of x1 will be replaced throughout by x1 plus minus x1 minus. For example, here we have x1, and then we replace it using the same expression. From a computational point of view, this approach has the disadvantage that the new equivalent model to be used has more variables than the original model. Fortunately, the approach can be modified slightly so that the number of variables is increased by only one, regardless of how many original variables need to be replaced. This modification is done by replacing each such variable xj by xj equals xj prime minus xj double prime, while here the x double prime is the same variable for all relevant j. So far we've discussed about the simplex method, and we talked about the standard form of the simplex method. And if in some linear program problems, if our constraints or the objective function or the non-negativity restrictions are not in the standard form, how to convert them into the standard form and then start the simplex method.